Welcome back to another video about game engine development with Vulkan. To distinguish bright light sources on a monitor, we can use a post-processing effect to make them glow. The light then bleeds around the light source. This light bleeding is achieved with an effect called bloom. In real life, you can see it on photos of strong light sources. We are trying to mimic this camera effect to create the same impression with our renderer. This video is brought to you by Lukas 1214 and I'm JC, aka Bowman Vienna. The algorithm presented in this video is based on a guest article from 2022 on Learn OpenGL. I put a link to the article in the description below. We translated this article to Vulkan and modified the approach to work on emissive materials rather than the whole scene. Lukas created the script of this video for the core implementation, and he implemented bloom in his DAXA-based render engine. I implemented the effect in my game engine Lucre, and this is what we're going to look at today. I put links to both implementations in the description below. This is how it looks like in Lucre. We have two test cubes, the damaged helmet from the GLTF examples, two test scenes, one for night and one for day. This is the day scene. There we have the emissive materials. One is a plain color, one is with a texture. Let's go back to the night scene. The moon and those two light bulbs up there are also emissive. The damaged helmet here. And this is how it looks like at night. The technique we're going to implement today is a post-processing effect called physically based bloom. It was presented at ACM Siggraph in 2014 by Jorge Jimenez for Call of Duty Advanced Warfare. Before we dive into the implementation, we'd like to give an overview of how it works. In theory, it's quite easy. First, we create an emissive image, which is MIP level 0, with 3 additional mipmaps. Each mipmap has half the dimensions of the previous MIP level. Feel free to experiment with the number of mipmaps. We're going to render all emissive materials into the emissive image during the deferred shading render pass. So MIP level 0 of our emissive image is part of the G buffer. Third, we downsample from the emissive image to the next smaller mipmap by using a filter. Then we repeat this step by downsampling the previous result into the next smaller mipmap until we reach the last MIP level. Fourth, we upsample from the last MIP level into the next bigger mipmap by using a different filter and by blending the result with what's in that mipmap already. We repeat this step until we reach the original emissive image. Fifth, in a post-processing composition stage, we add the bloom to our main 3-pass color output. We can take a look at this in Nvidia's Nsight tool. Here we are looking at the entire render sequence. We have 2 shadow passes and the main render pass. This is the downsampling pass with the color attachment. So here we see how we render the emissive materials one by one into MIP level 0. Here the downsampling starts by clearing and downsampling. And here we are upsampling until MIP level 0. For downsampling from one MIP level into the next one, we use a filter. This filter samples the current texel shown in the center of the picture. Additionally, it takes 12 surrounding samples. The filter assigns weights to all 13 samples, adds them together, and outputs them into the next smaller mipmap. The weights are color-coded in the picture, which by the way is taken from the original 2014 Siggraph presentation by Jorge. The texel in the center is assigned a weight of 0.125. Then one texel apart, the weight is 0.5 for all 4 texels, or 0.125 per sample. So for those 5 samples, we use 0.125 in the shader. 2 texels apart, we are using a weight of 0.0625 for the one in the north, east, south, and west, and half of that, so 0.0315 for the 4 texels on the outer corners of the sample area. For upsampling from one MIP level into the next one, we are going to blur the image so that we don't see blocky artifact. Our downsampling filter may produce another artifact, those are fireflies, which is a beautiful name for really bright pixels that can happen in HDR images. The up filter samples the current texel, and then all 8 texels adjacent to it applies a weighted distribution by using a 3x3 tint filter and writes the output to the next higher MIP map. The Vertex shader for the up pipeline and the Vertex shader for the down pipeline are identical. For each up or down sampled step, we issue exactly one draw call with a vertex count of 3 for one triangle. The vertices are generated by the Vertex shader, so we do not need a vertex buffer. For that, we use the Vertex shader intrinsic variable GL_vertex index. The triangle that we draw spans the entire normalized device coordinates, or NDC. So to downsample or upsample, we want to render a quad that spans the entire NDC. Here in this graphic, we have X going to the right and Y going down. The upper left is -1, -1. The bottom right is 1 and 1. And in the center we have 0, 0. If we look at the grid that is shown here, the far right upper corner is X equals 3 and Y equals -1. And the bottom left corner is X equals -1 and Y equals 3. Then we can draw one triangle that spans our entire quad from the upper left to the upper right to the lower left. Now that we know how it works, we can zoom out and take a look at the render sequence. This is where we left off last time. We had a shadow, a 3D and a 2D pass. The 3D pass is for deferred shading and has 3 subpasses for geometry, lighting, and transparency. In the geometry subpass, we render 3D models with different materials into the G buffer. In the lighting pass, we render into the main color attachment, which used to be provided by the swap chain. Now let's add post-processing. We add the emissive image to our G buffer and replace the swap chain image with a single color image. The emissive image must be RGBA float 16 because values are allowed to exceed 1.0. We clear it with the color black. Then we add a render pass for downsampling, one for upsampling, and one for composition. The difference between the down and the up render pass is that the down render pass clears its attachment, while the upsampling render pass just loads it. I realized only during the creation of this video that it may not be necessary to clear the render target during downsampling because the whole attachment will be written to anyway. You can try to use one and the same render pass for both up and downsampling and let me know in the comments if that worked. To render into targets with different dimensions, we provide a frame buffer for each upsampling and for each downsampling step. For the first downsampling step, we bind the emissive image, MIP level 0, with a descriptor for a sampler so that the fragment shader can read from it. Then we also bind a frame buffer that contains MIP1 as attachment. Then we can make our single draw call to the downsampling pipeline. For the next downsampling step, we start a new render pass that reads from MIP1 and renders into MIP2 and so on. After we rendered into the smallest MIP image, we can switch to the upsampling render pass and pipeline and make our way back up. For the first upsampling step, we bind MIP3 with a sampler descriptor, use a frame buffer that contains MIP2, and call the up pipeline. We repeat this until we reach MIP0, our original emissive image. The final composition stage, here depicted as a plus sign, samples from both the color attachment of the main 3D pass and from the emissive image. The pipeline of this stage renders with one draw call the entire NDC, as explained before. If the sample texel from the emissive map is not black, it will add it to the corresponding texel from the output of the main 3D render pass. Otherwise, it will simply copy the fragment from the 3D pass color output into the image provided by the swap chain. The new render system can be found under Engine, Platform, Vulkan, Systems, Bloom. The attachment class is a spec used to create the frame buffers and render passes. This here is an abstraction for frame buffers. This is a class for render pass abstraction, and this the actual render system. This header file contains the number of MIP levels. The attachment spec provides an image view and an extent to the frame buffer class, and the format, load store ops, and attachment layouts to the render pass. The frame buffer class takes care of the creation and destruction of a frame buffer with a single attachment. The render pass abstraction manages a render pass with a single subpass. It generates dependencies so that the previous pipeline completed the fragment shader stage, and the following pipeline waits for the color attachment output of the current render pass. And this is where the magic happens, the Bloom render system. It is using private functions to create image views, attachment specs, the render passes and frame buffers, descriptor sets and descriptor set layouts, a pipeline layout, and the up and down pipelines. There are also two helper functions to begin a render pass and set the viewport. In the constructor, the filter radius for the fragment shaders is set, and we take in references to the main 3D render pass and a descriptor pool. It creates the image views for the 4 MIP maps, then the attachment specs for the up and down render passes and frame buffers. It then creates the actual render passes and frame buffers according to those specs. Next, it creates a descriptor set layout and 4 descriptor sets for the MIP maps. For the 2 pipelines, it creates 1 layout and the 2 actual pipelines. For the magnification and minification filters for the samplers, we use VK filter linear. The up and down pipelines share the same layout. They do not need vertex buffers, so we clear the binding descriptions and attribute descriptions. For the up pipeline, we enable blending, set the color blend operation to add, and both the source and destination blend factors to 1. All these functions are called from the constructor. Here are the helper functions. And finally, the public function render bloom. It binds the down pipeline and then loops over the 3 downsampling stages. For each stage, it begins a new render pass, sets up a viewport, push constants with the filter radius and the current resolution, binds the descriptor set for the current MIP level, issues a draw call for 3 vertices, and ends the render pass. For upsampling, the code is accordingly. I added a slider with IMGUI to adjust the emissive strength. Press M to bring it up, use to use it. Then if we go all the way to 1, it becomes white hot glowing. 0 is the base color. And 0.35 is what I found looks best. We can also adjust the moon. Crank it up some more, or make it more subtle. And there we go. Alright, that's our take on the Bloom topic. We hope you enjoyed it as much as we did. Maybe you got some inspiration out of this video. If you have feedback, please leave a comment. Please like this video and subscribe to my YouTube channel. And also, if you have a GitHub account, please like our projects. Here are the links again. By the way, you can find us on Discord on Brendan Galea's Vulkan game engine development channel. Thanks for watching and have a good one.